So I'll start. Okay. So first of all, I would like to thank the organizers for bringing the community together every year. It's really a very nice feeling and an experience each time. So this is the title of my talk. I'm going to talk about some very recent work on ferronematics. And that's the broad plan, bit of an introduction, the methodologies and results, and if possible, a summary. So this work has been primarily done with two graduate students, Aditya Vats, who's in the audience and also has a poster, and Konarak Bist, who's currently writing his thesis. And also in collaboration with Sanjay Puri. It's also part of a DST UKD project. So Appala Muzumdar and Paul Milevsky, they are my partners in the UKD project. Okay. So, something that many of us already know. So liquid crystals, they are intermediate between conventional liquids and solids. And they're an interesting system which combine fluidity with long-range orientational order. Okay. So in the nematic phase, that's the ordered phase. So you have an isotropic phase and a nematic phase. So in this particular phase, the calamatic or discotic molecules, they self-align to have a directional order, but there's no positional order in this system. Okay? One can see from this particular cartoon here. Okay? And the average orientation of liquid crystals is described by a sign invariant unit vector, which is known as the director. Okay? Now, one of the reasons why these materials have been very, very popular is because they have very fast optical response even to very tiny electric fields. And that's the reason why they are being exploited and in liquid crystal displays, optical switches and optical imaging devices. Okay? But they have a very small magnetic susceptibility of the order of 10 raised to minus 7, and hence very high magnetic fields are required for actuating them. Okay? To be able to, to have them used in magnetic based devices. Okay? So way back in 1970, Varsha and de Genes, in very pioneering work, they proposed that one could include a small quantity of magnetic nanoparticles in NLCs and make them sensitive to a magnetic response. Okay? So what they argued is that the MNCs, they will couple to the nematic liquid crystal molecules via surface anchoring, and then you can manipulate the surface, manipulate the system by virtue of external magnetic fields. Okay? In experiments, however, it was found that the magnetic nanoparticles, they aggregate within tens of minutes due to dipole-dipole interactions. Okay? So liquid crystals with nano-inclusion were found to be unstable and just remained a theoretical construct. Okay? But recently in 2013, the Slovenian group of Alenka Mertelj, they created the first stable suspension using barium hexaferrite platelets in nematic liquid crystals. Okay? So the stability of the solution is closely related to the shape of the nanoparticles. And what they found is that if they used homeotropic anchoring, that is if the liquid crystals align perpendicular to the surface of the particles, okay, there's formation of what are called as Saturn ring defects, and these were quadrupolar defects, and they had a charge -1. So this defect repulsion, it counteracted the dipole-dipole interaction between the magnetic nanoparticles, and that was wonderful. So ever since, this fascinating class of materials, which is now called ferronematics, it's enjoying a lot of interest from academia as well as industry. And here's a little cartoon of the stable suspension. Okay, these are the Saturn ring defects. The particles are perpendicular to the director. Okay? And these are measurements of hysteresis. So as one can see, if you increase the concentration of particles, one can see very nice hysteresis loops. Okay? Now a little bit about phase ordering, because the study is primarily about phase ordering. So let's consider a rapid quench of a magnet from t greater than Tc to t less than Tc, and let me call that as time t equal to 0. So I'm going from here to here in the absence of the field. Okay? So what's going to happen now? The domains of upspins, let's consider something like an Ising system. So the domains of upspin and downspin are going to form. These domains will coarsen with time, okay? And the coarsening is driven by domain walls or defects. Okay? And quickly going to mention only certain things without any proofs. So in systems with non-conserved kinetics, such as the Ising model, domain growth obeys what is called as the Lifshitz-Alan-Kahn law. That is L of t, that's the characteristic size of the domain. L of t goes as t half. Whereas in systems with conserved kinetics, like in the binary alloy, domain growth follows what is called as the Lifshitz-Lyasov law. So this is the t raised to 1/3 law. Okay? So in most of these problems of coarsening, these are the important questions. What is the domain growth law and what is the nature of defects? Okay? So now I come to the system that we have. So we have nematic liquid crystal molecule and we have the magnetic nanoparticles put in it. Okay? So the framework is the Landau-de Genes free energy framework. Okay? So that's my local free energy. It depends on two order parameters now. One is Q and one is M. Q is what describes the nematics. Okay? So that's a tensor and it contains information about the orientational order of the nematic, and one can actually relate it to the directors. Okay? So you can evaluate what is Qij by knowing what are the directors at positions I and J. Okay? And this S is a scalar order parameter. It actually measures the fluctuations about the director. Okay? Then we also have the magnetization. Okay? That's the spatially averaged magnetic moment of the suspended nanoparticles. So let's go back to the free energy. This is the part which is coming from the liquid crystals. That's the part which is coming from the magnetic inclusion. And this is the coupling between the nematic and the magnetic terms. Okay? So these are coefficients which can be determined experimentally. Okay? So we are interested in studying the dynamics. So that is that is governed by these coupled TDGL equations. Okay? And I already see that I'm running out of time. But in this, these are the damping coefficients, and one can very easily obtain a dimensionless form of the TDGL equation by doing certain scalings. Okay? So that's how the TDGL equations for d equal to 2 look like. The important thing to note is that so now we've converted, we've rewritten the parameters in terms of the Landau parameters. Okay? So there are four constants here, C1 and C2, which are related to the coupling between the two components. That's the gamma, which is the coupling term. And then there is this relative diffusion term and there's the relative damping coefficient. So what we have done for simplicity is set these as equal to 1. So the only parameters in the model at the moment are the coupling constants, okay? C1 and C2. And these are the different cases of interests. So you have two components. So there are the critical temperatures of these two components in their uncoupled state. So let me call them as TCN and TCM. And then there are these different coupling limits, that is C1 equal to 0 and C2 not equal to 0 and vice versa, and when the two couplings are identical. Okay, so we perform different kinds of temperature quenches and study the effect of the magnetonematic coupling C1 and C2 on morphologies and growth laws. And of course, these are idealistic situations, but they are typically true when the couplings are weak. Okay? So Aditya has very painstakingly worked out all the stable solutions. He's been able to do that, and it's very nice to work them out because they determine the magnitudes of all components in the model and limits on the different model parameters for stability, etc. Okay? So that's the first picture that I have. These are the coarsening morphologies of the nematics, and these are the coarsening morphologies of the magnetic component. Okay? And what's the temperature? The temperature is such that now the magnetic component can order, but the nematic cannot order because T is above TCN. And we have this particular coupling, and we've done various couplings, but I'm choosing this one, okay, where now the magnetic component is coupled, the nematic component is coupled with the magnetic component and not vice versa. Okay? So one of the interesting things that one sees here, and this is at time t equal to 10 some units, and this is 10 raised to 3. So what one sees is that M and N always co-align. Okay? So here, you can take a look at the color coding here. So when the nematics are pointing in the first and the third quadrant, we color them blue. When they are pointing in the second and the fourth quadrant, they are green. But now the magnetic moments, they have an up-down symmetry. They don't have this up-down symmetry like the nematics. So then you require 4 colors for them. That's blue, that's green, red and yellow. Okay? So blue and red, they correspond with the blue in the nematic. Green and yellow, they correspond with the green in the nematic. Okay? So one can see that there is always this co-alignment. N is parallel to M or N is parallel to minus M. And there is this microstructure due to the up-down symmetry of the magnetic moment. Okay? And meeting of all colors typically indicates a vortex. And these, we find that all these magnitudes agree very well with the analytic calculations. So what's the moral of the story here? There's slaved coarsening of the nematic with the ordering magnetic phase. Okay? So the magnetic phase is supposed to order because of the quench that has been chosen. But because of the magneto-nematic coupling, the disordered phase of the nematics, liquid crystal molecules, which is the isotopic phase, that is forced to order, and that's what we are calling as slaved coarsening. Okay? About the growth laws, now there are different cases that we've considered. So in some cases, we've observed the T-half law, and in some cases, we've observed the T1/3 law, which is characteristic of conserved kinetics. That's unusual over here, but we have some hand-waving explanations for this, and I'm sure if you visit Aditya's poster, you'll be able to get explanations to many of these things. And that's another interesting morphology. So this is when the temperature is below the critical temperatures of both, and here one finds that there's a nice subdomain structure. That's happening because of the lack of up-down symmetry of the magnetic moments. So in this case, some of the scattering properties are a little different because in both these systems with two with vector order parameters in dimension d equal to 2, one should expect a tail of the structure factor which goes as k raised to minus 4 because it's 2 plus 2. Okay? But for this part, we are observing something like k raised to minus 3, which is characteristic of interfacial defects, okay, for the magnetic part. Okay? And that's something that was observed in the experiments of Mertels et al. So it's very similar to the morphology that we've got here, which also tells us that many of the features we have included in our very coarse-grained and simplistic model, they seem to be correct. Okay? And that's some work with Konark Bis and Appala Mazumdar. Okay? So here we put the system in confinement, and in this case we took different diffusion constants for the two components, and we found that by playing around with these 4 parameters, we could tailor and manipulate defects and create bistabilities in these square wells, which are actually being called as pixels for futuristic displays. Okay? So that's the summary. I'll leave you at that since I've run out of time, and maybe I'm happy to answer a question or two.
We have time for one question.